So here we are going to discuss two questions. Both are based on a desk calculator grammar. Uh, the first question is that consider the following grammar and give the syntax directed definition to construct a parse tree for the expression this and construct an annotated parse tree according to your syntax directed definition, and grammar is provided here. Okay, this question is asked in AQT 2010 and 11, and almost same question is asked in 2013 and 16, and here grammar is not provided in the second question. Okay, so today we are going to discuss both questions. So I would like to recall the designing procedure of an SDT. Whenever we are going to design any SDT, our first task is to assume the string and then draw the parse tree according to the given grammar if grammar is provided in your problem. Okay, so in the first question, grammar is provided, so our task is to assume any string which is generated by this production. So you can see here, uh, in my first question uh, the string is already provided, so in the first question we don't have a need to assume the string. Okay, we will follow a particular string, 4 into 7 plus 1 into 2. So if we are going to design a parse tree, so such type of parse tree we will design with the help of given grammar, uh, 4 into 7 plus 1 into 2. So this is our desired parse tree, and with the help of this parse tree we are going to design SDT. Okay, and you can expect your answer 4 into 7 means 28 plus here 1 into 2, 28 plus 2, 30. So the final answer we could expect here is 30. So the first reduction which is going to perform in this parse tree is this one. The next reduction is t tends to f. The third reduction is f tends to num. Fourth reduction is t tends to t into f. This is the fourth reduction. Fifth reduction is e tends to t. Sixth reduction is f tends to num. Seventh reduction is t tends to f. Eighth reduction is this one. Ninth reduction is t tends to t into f. And the last reduction is e tends to e plus t. So the total number of reduction here is total 10. So when we are going to reduce a first reduction f tends to num, it means at that time this 4 value is stored here in that node. It means the f dot num means f dot num. The SDT for f dot num is nothing but, sorry, f dot value means we are going to assign a value at a particular node f. So the SDT for this node is f dot value equals to num dot l value, because leaf node value is provided by the lexical value, so num dot l value is here. So you can see in my answer f dot num is f dot value equals to id, or sorry, this is actually a num. This is actually a num because in our grammar num is provided, so we will use a same term num dot value. If id is provided here, so you can use it id dot, sorry, id dot l value. Okay, so the first SDT is designed, and if we are going to reduce a second means t tends to f, so the value 4 which is stored here is exactly transfer here. So the SDT for this production is the value of f is transfer into the node t. Okay, the next reduction is f tends to num again, so the same SDT is occur and the value 7 is stored here. Then after t tends to t into f, so the value of this node means 4 and the value of this node is 7, and we are going to perform multiplication operations. So the SDT for this t tends to t into f is the value of left child is multiplied with the value of right child. So here you can see that t tends to t into f is nothing but t dot value equals to t dot value into f dot value, means 4 into 7, this is a 4. If I am correlating with this reduction, so at that time this is a 4, but it is not a fixed. So 4 and 7, and that is a 28. So 28 store here. Again same 28 value is move here. So the next reduction, so the next SDT is the value of t node is directly assigned into the node E. So here this SDT is designed. We have already designed 4 SDT rules, and then after we move here, SDT is already designed, so the value is 1 stored here. Then after this same value is stored here with the help of this reduction rule. After that, two values assigned here, and then t tends to t into f means left child value is multiplied with right child value, means here the value is 1 and here the value is 2. So 1 into 2 is 2. So this is stored here with the help of this SDT rule. And the last is e tends to e plus t, means left child value is adding with right child value, and here is the value is 28 and here the value is 2. So 28 plus 2 is 30. So finally we will get a 30 answer in that case. So the SDT for the last production is e dot value plus t dot value assigned into the e dot value. So this is the solution of the first question. And so now we are going to discuss or solve the second question. So the difference between first question and second question is that in this question grammar is not provided. So first of all we will assume the grammar which generates such type of string, and then we are going to design SDT for a desk calculator grammar. Okay, so whenever such type of question is provided, our first task is to assume the grammar. So here I have already mentioned assumed grammar. You just look at here what is the string provided in this question. 4 into 7 plus 1 parenthesis multiplication with 2. So in this string there are some operator. The first one is a plus, next one is a multiplication, and the last one is a left and a right parenthesis. So you just define the production. The first production is e tends to e plus e, means in this production we have assigned a plus operator, in the next production we have assigned a multiplication, and in the next production the production is e tends to parenthesis of left parenthesis e and right parenthesis, and the last production is e tends to num, is this num is provide the particular value. Okay, uh, why we use ambiguous grammar here? So because the assumption of ambiguous grammar is easy compared to unambiguous grammar. So whenever in your question grammar is not provided, so you simply assume a ambiguous grammar. Suppose if in this expression something minus, division and so many operators are introduced here, so you can create another production for a particular operator. So it is a simple procedure by which we can assume a grammar for any string. So after the assumption of a grammar, we are going to design the parse tree for a particular string, means left parenthesis 4 into 7 plus 1 parenthesis close multiplication 2. So the desired pass trees look like this: 4, 7, 4, 7, and what is this? Yes, there is 1. 4, 7, 1, and 2. I think you all of understand how to draw the pass tree. Here E is missing in this node, and there is some multiplication operation is also missing. So make it clear. So after designing the pass tree for 4 into 7 plus 1 into 2, on the behalf of this grammar, we are going to design SDT. So you all of are known how to design an SDT. First of all, we will assign, or we will calculate the order of reduction which is going to perform in this pass tree. The first reduction is this one, second reduction is this, third reduction is E tends to E into E, fourth reduction is this one, uh, fifth reduction is this, sixth reduction is this, seventh reduction, and the last one is a eighth reduction. Okay, and if you are going to evaluate the expression, so 4 into 7 is nothing but a 28, 28 and plus 9. So here this is a 29, and this expression is evaluated because the parentheses apply here, and then after we are going to add multiply 2. So for 4 into 7, 28, plus 1, 29, and 29 into 2 means it is 58. So such type of answer we are expecting from our SDT. So start the designing of SDT. Here the value of this node is 4. So in that node we will assign E dot value equals to num dot L value. You can see here E dot value equals to num dot value. So here you can see that E dot value equals to num dot L value. The work is simple here, and in this reduction the same 7 value, or the value of this leaf node, is assigned here. So in the left child the value is 4, and the right child the value is 7, and if multiplication operation is occur here, so in the next reduction E turns to E into E, the left child value is multiplied with right child value. So the SDT for E tends to num already have discussed, and the SDT for E tends to E into E is E dot value equals to E dot value into E dot value. So here you can store the value 28. Okay, after that we are going to reduce E tends to num here, and the value is 1. So the same value 1 is assigned here, and after applying a plus operation, 28 plus 1, 29 is stored here. Okay, so the SDT for E tends to E plus E is E dot value plus E dot value. So you can simply design it. Now here the value is 29, and the same 29 value is transferred here, because in this level and that level there is no additional operation is going to perform. So the value is not changed from this node to this node. It means after applying this reduction, E tends to left parenthesis E and right parenthesis, same E value is assigned here. So here the value is 29, and then after the left child value is multiplied with right child value. So here SDT is already decided, E tends to E into E. So the E dot value into E dot value, the value is here is 58. So this is all about SDT for a second question.